Hi, we know how to fit a line to data now. Now the question is, should we have done that in the first place, or how good is the line that we fit? Many relationships in science are exact. Distance is rate times time, energy is mc squared, famous Einstein equation, force is mass times acceleration. Many relationships in business, though, are inexact. They have noise in them. How do we express uncertainty on our relationships? How do we put noise in the model? Well, here's the a chord regression output again. So we're modeling the price of a chord as a function of the mileage, odometer. And the question is, we get output here. We get a B0 and a B1. And you might say it's an exact relationship. Here's our B0, here's our B1, that's the intercept and slope. We might say the price is 17,067 minus 0.06 times odometer. For every additional mile on the car, the price goes down by 6 cents. But this, just staring at it, is an exact relationship. Now I don't have it here, but if we go back and we look at actually the scatter plot, we know it's not an exact relationship. An exact relationship would mean that for each x, there's a single y value. But there were points, and if you go back in the scatter plot, you'll see there are points that for around the same x value, there was two different y values. And so you don't have an exact relationship when you look at your data set. It's inexact. How do you interpret this, first of all? Well, in regression, we actually say what we're modeling is the average car price. In regression, we're modeling the average value of y as a function of x. So we would interpret this not as price is 17,067 minus 0.06 odometer. That's an exact relationship. We would interpret it as the average car price is 17,067 minus 0.06 odometer. And that's what we're doing in regression. We're modeling the average value of y as a function of x. So as we see here, like let me see an example here. So around this shows you it's not an exact relationship. If it was an exact relationship, you get the same y's here, but you're not. So this is a model of a sort of linear model with noise in it. And we think of this line as the line of averages. We can also call that the E of y given x, the average value of y given a value of x. But we think of the regression line as a line of averages. We can write it theoretically like this. This says the average value of y as a function of x is beta 0 plus beta 1x. That's one way to think of it. I like looking at it this way. This says, what's our data generating process? What produced our y's? And this is an expression that says y is a line in x plus epsilon. And what is epsilon? Epsilon is some sort of noise. If there's no noise in the model, this would be an exact relationship, but epsilon refers to the fact it's an inexact relationship between y and x. Beta 0 is the population intercept. Beta 1 is the population slope. Now here's the thing, they're true but unknown. We're going to collect data and form guesses on them. It actually might be beta 0, 0. It actually might be beta 1 is 0. What would it mean if beta 1 were 0? It means there truly was no linear relationship between y and x, and that's a question we want to know. But this is what we think theoretically is going on. We collect data, and then we get guesses of beta 0, guesses of beta 1, and we can see what's going on. What does our data tell us about the population values? What do we assume about the noise? We assume the noise is normal 0 with variance sigma squared, standard deviation sigma. That's a very important number. The sigma is a very important number that tells me how much noise is in the system. The larger sigma is, the more noise in the system. The smaller sigma is, the smaller noise in the system. And the mean 0 tells me that half the time the noise is above 0, half the time it's below 0. On average, the noise is 0. So these are called assumptions of the linear regression model. We assume y is a linear function x. We assume there's noise in the model. We assume the noise is normally distributed. We assume the noise is not related to the x. That actually would cause problems if that were true. And we assume the noise is normal, mean 0, and standard deviation noise is sigma. The variance of the noise is sigma squared. These are population quantities. We have to estimate them. We fit a line of data using the method of least squares. B0 is our guess of beta 0. B1 is our guess of beta 1. Those are just the least squares estimates from before. Note, B0 is not beta 0, it's a guess. B1 is not beta 1, it's a guess. The EIs, the errors, the residuals are not the epsilon i's, they're just guesses of everything. Greek letters always refer to population quantities. The American or Latin letters, whatever we call B0, B1, EIs, those are not population quantities, those are sample quantities. And finally, we want to get a handle on what sigma is. This is very important because it's going to help us determine how good our guesses are, how good our predictions are. And sigma is essentially how much noise is around the line. This is small sigma, of course, not a lot of noise. And over here would be large sigma, a lot of noise. So how do we know whether or not we have good or small noise? I mean large or small noise in the model. We have S sub B. S sub B is defined by this, and this is a guess for how much noise is in our system. So we take the sums of squares errors, divide by n minus 2, and that's our guess of S of B squared. Square root of that's our guess of S of B, and this is probably the most important number on the output because this tells me how good my predictions will be. Where do we find that? In R, it's called the residual standard error. It's called S of B, and over here it's given by 303. Now the units of S of B are the same as units of the Y variable. So in this case, price is in dollars, S of B is also in dollars. For the Pharmex data, where we find this again, so the residual standard error is 7.39. Here's an exact relationship. This is temperature around the world in Celsius, temperature around the world in Fahrenheit. Looks like an exact relationship. R squared should be, 1. Sorry about that. I was thinking ahead. R squared should be 1. What should S of B be? Should be about 0, and that's what you see. That's 1.38 times 10 to the minus 15, and that is indeed about 0. For something like this is SAT versus pulse. Looks like a stupid thing to do. The SAT should not be related to your pulse rate, and it looks like there's no relationship whatsoever. What should R squared be? In this case, R squared should be 0, and S of B in this case is not 0. It's some large number. That tells me there's a lot of noise in the system. What does it mean for S of B to be a large number or a small number? In general, we want this to be true. We want S of B to be a lot less than S of Y. This is the inherent variation in Y. This is in the noise. After we use X to explain what's going on, this is the leftover noise. This is how much is not being explained. We want that to be really small. 0 would be perfect. It's generally not going to be 0. But it's telling us how good is our model fitting. What do we use this for? Well, this is the answer here, called prediction intervals. And we have a horrible graph that really doesn't give you any more educational information here. It's just a graph I made 30 years ago, and I call it my lucky bamboo graph in the middle there. And it's not educational, but I keep it in for sentimental reasons. But let's do this with an example. You use S of B when you do prediction intervals. You want to know how good your guess is. So when I look at S of B, what I do is I look at plus or minus 2 S of B. And that tells me how good my predictions are going to be. And so this is 303. I double it, that's 606. And this says if I use my model for predictions, my predictions will be plus or minus $606. Now, to me, that makes a lot more sense than talking about R squared and adjusted R squared. So if you tell a client, yeah, we fit a regression model, we got an adjusted R squared at 64.7 or 65% for R squared, your client's like, is that a good value? Is that a bad value? Well, it's between 0 and 1. Closer to 1, the better the model, blah, blah, whatever. You're going to come up with your explanation for R squared. And doesn't really tell how good predictions are. And that's usually why people are fitting these models. And so we just take S of B, we double it, and we go, yeah, if you use this model for predictions, your predictions will be plus or minus 606. Then that's up to you. Are you happy with the plus or minus 606? Do you want it to be higher, or do you want to be lower? And so it's a great number to look at. And here we're showing you doing that. We want to predict the price of a 50,000 mile Accord. We plug and chug it in. We do plus or minus, 1.96. We round it up to 2. And we're pretty sure, we're 95% confident, the true price of an Accord with 50,000 miles is somewhere in that interval. It's called a 95% prediction interval. So you can see price versus miles per gallon. Miles per gallon is not as good a variable. R squared's way lower than before. And if we do this, our prediction is going to be plus or minus around 5240 or so. A lot worse than 606. So it says, worse the model, higher S of B, higher prediction error. Better the model, the lower S of B, the lower your prediction error. And again, what do we have going on here? There are two different intervals. If you didn't collect X at all, if you knew nothing, and someone said, oh, what's the next Y going to be? Predict the price of a car. You would say, average price plus or minus 2 S of Y. That's just no X knowledge whatsoever. The idea is that knowing X, you should have better predictions. And so your interval would be, that should be Y hat. Y hat plus or minus 2 S of B. You should have better predictions. And so we want this to be happening. We want S to be much lower than S of Y, narrow prediction interval. Let's understand what's going on with the noise in the model. What's the role of the noise in the regression model? Well, here we have 6 graphs. We have 6 situations here. And what should be happening? As you add more and more noise to the model, it's going to be harder to find the line. Less noise, easier to find the line. So if we put letters here, A, B, C, D, E, F, this is clearly A. And then D would be this, F would be this, E would be which, sorry, the last one, A, B, I'm just saying, the last one, the next one would be B. Now the last two, we have this to figure out and this to figure out. How do you do it? One's got a little bit of noise, the other's got more noise. Well, you look at the y-axis. Which one has a bigger y-axis? Visually, they look very similar, but this has a much bigger y-axis over here. So it goes C and then E. But the idea behind all this is that you add more and more noise to the model, it's harder to find the line. There's a line in there, but the noise overtakes the line. In the next video, we'll talk about how sure are we? How do you build confidence intervals for B0 and B1? Thank you, and I hope you're having a great day.